The universe is keeping its biggest secrets hidden in plain sight. For all our telescopes and theories, most of the cosmos remains a complete mystery, an invisible puzzle with most of its pieces missing. But what if the key to solving it has been lurking in the shadows since the very first moment of time? I am talking about primordial black holes. These are not the black holes formed from dying stars that you know. These are hypothetical relics forged in the chaotic furnace of the Big Bang itself, and they might just be the master key to unlocking everything. By the end of this, you will have a front row seat to 25 theories that could completely rewrite the rules of reality. Could the missing 85% of all matter be made of ancient black holes? Is there a tiny, planet-capturing black hole hiding in our own solar system? We are about to take a wild ride from the birth of the first stars to the edge of the multiverse, all guided by one astonishing idea. What cosmic mystery would you most want to solve? The most audacious theory of all suggests we have been looking for dark matter in all the wrong places. Forget exotic, undiscovered particles. What if the answer has been hiding in the darkness since the universe was a newborn? Theory number 1 proposes that primordial black holes are dark matter. This is the idea that the invisible glue holding galaxies together, the mysterious 85% of all matter we cannot see, is not made of some strange particle. It is made of ancient cosmic fossils. These would not be the colossal black holes at galactic centers. They would be far smaller, ranging in size from a mere asteroid to perhaps a small planet. Imagine a black hole with the mass of Mount Everest but compressed into a space smaller than an atom. Or picture one with the mass of Earth hidden in the void between stars. Their sheer age and tiny size make them nearly impossible to spot directly. They are the ultimate cosmic ghosts drifting through space, their immense gravity subtly tugging on everything around them, yet leaving almost no trace. This solves a major puzzle. For decades, physicists have searched for weakly interacting massive particles, or WIMP, hypothetical particles that barely interact with normal matter. But despite enormous sensitive detectors buried deep underground, we have found nothing. Primordial black holes offer a compelling alternative. They are not particles that avoid detection. They are objects so compact and dark that they simply slip through our nets. They do not emit light. They do not collide with atoms in a detector. They just drift, their collective gravity sculpting the cosmos on the grandest scales. If this theory is correct, then every galaxy, including our own Milky Way, is swimming in a vast, invisible sea of these primordial relics. Every time a distant star's light flickers from an unseen gravitational lens, it might not be a passing planet causing it. It could be one of these ancient shadows, a whisper from the first second of time, silently shaping the universe we see today. But that is just the beginning of their cosmic influence. If primordial black holes are the invisible scaffolding of the universe, then they might also be the architects of its most terrifying structures. Theory number 2 suggests they seeded the supermassive black holes. At the heart of nearly every large galaxy, including our own, lies a monstrous gravitational pit. These are the supermassive black holes with masses millions or even billions of times greater than our Sun. And here is the puzzle. We have observed these giants in galaxies that formed when the universe was incredibly young, barely a few 100 million years old. That does not give them enough time to grow from the collapse of a single massive star. It is like finding a fully grown oak tree sprouting from a crack in the sidewalk just days after the concrete was poured. The timeline simply does not work. So how did these galactic titans get so big so fast? Primordial black holes offer an elegant and almost obvious solution. They are the ready-made seeds. Imagine the early universe still hot and dense. Within this primordial soup, pockets of extreme density could have collapsed directly into black holes of all sizes. Some might have been born already thousands of times more massive than our Sun. These are not the asteroid-sized dark matter candidates. These are the heavyweight champions, the cosmic royalty. They would have been present from the very first moments, providing a massive head start. As the universe expanded and cooled, ordinary matter, drawn in by the immense gravity of these primordial seeds, would have begun to swirl around them. Gas clouds would have collapsed, stars would have formed and died, all feeding the growing darkness at the center. The primordial black hole did not need to start from scratch. It was born with a running start, a massive core around which an entire galaxy could slowly assemble itself. Without this seed, explaining the existence of ancient supermassive black holes becomes a frantic race against time. With it, the story gains a natural beginning. Every colossal black hole we see at a galaxy's heart, every invisible engine powering brilliant quasars in the distant past, might trace its lineage back to a single, random fluctuation in the fabric of newborn space. The universe's first dawn was a long, silent one. After the Big Bang's blinding flash, the cosmos expanded into a vast, dark, and nearly featureless sea of hydrogen and helium gas. It was too smooth, too uniform. For stars to ignite, you need knots of higher density, seeds for gravity to work its magic and pull matter together. But in that perfect primordial fog, those seeds were scarce. So how did the first stars, the brilliant beacons that ended the cosmic dark ages, ever manage to light up? Theory number 3 offers a startling catalyst. Primordial black holes drifting through those ancient gas clouds could have been the universe's very first matchsticks. Picture one of these ancient objects, perhaps with the mass of a large asteroid or even a planet, moving silently through the primordial gloom. It is a perfect gravitational nucleus. As it travels, its intense gravity acts like a cosmic snowplow, silently gathering the thin gas around it. Hydrogen atoms begin to swirl into a disk, colliding, compressing, and heating up. This process is called accretion. The black hole itself does not need to be large. Its power lies in its extreme density. It creates a focal point, a deep well in the fabric of space that the surrounding gas cannot resist. Without such a seed, the gas might have remained diffuse for hundreds of millions of years longer, slowly clumping under its own weak gravity. But with a primordial black hole present, the process gets a violent head start. The gas compresses faster, heats up sooner, and reaches the critical temperatures and pressures needed for nuclear fusion in a fraction of the time. In this scenario, the first stars might not have formed in isolation from random gas clumps. They could have ignited like fiery halos around these invisible, drifting anchors. The black hole would sit at the center of a newborn solar system, a dark heart around which the first light in the universe burst into existence. Some of these early stars, feeding from the rich reservoir of gas funneled by the black hole, might have grown monstrously large and lived short, violent lives. Their explosive deaths would then have seeded the cosmos with the first heavy elements, the carbon, oxygen, and iron that would later build planets and life. So the very chemistry of our world might trace back to the gravitational whisper of a primordial black hole, a dark seed that sparked the first dawn. The crackle of a cosmic mystery echoes across the universe in a single, blinding millisecond. Fast radio bursts are among the most bizarre signals we have ever detected. These are not the steady pulses of a spinning neutron star. They are colossal explosions of radio wave energy, brighter than entire galaxies, that flare into existence and vanish before you can blink. Their source has remained one of astronomy's greatest puzzles, but theory number 4 offers a spectacularly violent possibility. Primordial black holes might be the hidden triggers of these cosmic fireworks. The idea hinges on a catastrophic encounter. Imagine one of those ancient asteroid mass black holes, a dark wanderer from the dawn of time, on a collision course with a neutron star. A neutron star is the incredibly dense, city-sized corpse of a giant star, a place where a sun's worth of mass is crushed into a sphere just a few miles across. The physics of such a meeting are almost unimaginable. As the tiny, ultra-dense black hole plows into the even denser neutron star, it does not simply make a crater. It tunnels. It would pierce the neutron star's surface like a bullet through tissue paper, sinking straight toward its core. This creates a shockwave of unbelievable energy, rippling through the star's intense magnetic field. The disturbance is so violent, so sudden, that it could launch a focused beam of radio waves powerful enough to be seen across billions of light years. In a literal flash, the signal is born and then it is gone, leaving the neutron star perhaps permanently altered, its internal structure ravaged by the dark intruder. This model fits the observed profiles of many fast radio bursts perfectly. The event is inherently one-off and catastrophic, explaining why we rarely see repeats from the same location. The energy released matches the staggering output of the bursts, and it provides a natural reason for the signal's incredible brevity. The entire disaster, from impact to energy release, happens in a cosmic instant. There is another, even more exotic possibility linked to the end of a black hole's life. Stephen Hawking theorized that black holes are not completely black. They should slowly evaporate, losing mass over astronomical timescales by emitting radiation. For a stellar mass black hole, this process takes longer than the current age of the universe. But for a very small primordial black hole, with the mass of a mountain or less, the final moments would be spectacular. As it nears the end of its evaporation, it would not fade away quietly. It would explode. In its last fraction of a second, the tiny black hole would release all of its remaining energy in a tremendous burst of particles and radiation. Some models suggest this death scream could also manifest as a fast radio burst, a final, brilliant flash marking the end of an object born in the universe's first second. So the next time astronomers detect one of these fleeting, universe-spanning signals, they might not be witnessing the birth of something new. They could be observing the violent death of one of creation's oldest relics, or the catastrophic marriage of a dark ancient seed and a stellar corpse. Our own solar system holds a gravitational secret in its frozen outer reaches. For years, astronomers have tracked the strange, clustered orbits of small, icy bodies far beyond Neptune in the region we call the Kuiper Belt. Their paths are oddly tilted and bunched together, as if being shepherded by an unseen force. The leading explanation has been a hypothetical planet 9, a world perhaps 5 to 10 times the mass of Earth lurking in the perpetual twilight. But theory number 5 proposes something far more exotic. This hidden shepherd is not a frozen planet at all. It is a primordial black hole, not a monster but a tiny, dark relic. With a mass of 5 Earths compressed by its own immense gravity, it would be no larger than a grapefruit. Picture that for a moment, an object with enough gravity to tug entire worlds, small enough to hold in your hands. This solves several puzzles at once. A planet of that mass would likely glow faintly with leftover heat from its formation, and our infrared surveys have found nothing. A black hole, however, is the ultimate cold, dark object. It emits no light of its own, making it perfectly invisible to our telescopes. Its only signature is its relentless gravitational pull, which matches the observed shepherding of the distant Kuiper Belt objects perfectly. So how could we ever hope to find such a minuscule speck of darkness in the vast expanse? One proposed method listens for a whisper of annihilation. If this black hole is indeed a relic from the Big Bang, and if such relics make up dark matter, then it would be surrounded by a dense halo of dark matter particles. As these particles collide and annihilate each other in the black hole's intense gravity, they could produce a faint but detectable stream of gamma rays. Our orbiting gamma-ray telescopes could, in theory, pick up this unique signature, a steady, pinpoint glow against the cosmic background, revealing the black hole's location. Another method is more direct, and it involves watching for flashes. If a small, distant object like a comet or asteroid were to pass too close to this grapefruit-sized singularity, the extreme tidal forces would shred it apart in an instant. The debris, heated to incredible temperatures as it spiraled into oblivion, would flare brightly for a short time. Astronomers have proposed scanning the sky for these sudden, unexplained accretion flares in the outer solar system. Finding one would be like seeing a single match struck in a dark forest, revealing the presence of the hidden hunter. The implications are staggering. It would mean our cosmic neighborhood, the place we call home, hosts a fossil from the universe's first second. This tiny, ancient shadow, silently orbiting our sun, would be the most tangible evidence ever found for the primordial black hole hypothesis, and a constant gravitational reminder that the deepest mysteries of the cosmos might be hiding in our own backyard. The chemistry of the cosmos is written in the first 3 minutes. In that blindingly hot, dense dawn after the Big Bang, protons and neutrons fuse to form the universe's first atomic nuclei, a process called Big Bang nucleosynthesis. The predictions from this primordial alchemy are spectacularly accurate for the lightest elements. The amount of hydrogen and helium we see across the universe matches the theory almost perfectly. But there is one glaring, stubborn exception: lithium. According to the calculations, the newborn universe should have left behind about 3 times more lithium-7, a specific isotope, than astronomers actually observe in the oldest stars. This is the cosmological lithium problem, a quiet but persistent crack in our otherwise solid understanding of the universe's first moments. Where did all that lithium go? Theory number 6 suggests the culprits were dying primordial black holes, evaporating in a final blaze of glory and rewriting nuclear history. To understand how, we need to revisit the end of a small black hole's life. As Stephen Hawking predicted, black holes slowly lose mass and evaporate. For a tiny primordial black hole born with the mass of a small asteroid, this process would have concluded relatively quickly, within the first few minutes or hours of the universe. Its death would not be quiet. In its final instant, the black hole would explode, releasing a tremendous burst of high-energy radiation and particles into the surrounding primordial soup. This sudden injection of energy is the key. The early universe was a seething cauldron of nuclear reactions, with protons and neutrons constantly fusing and breaking apart. The explosion of a primordial black hole would flood its immediate vicinity with a torrent of neutrons. These extra neutrons would have acted like a chemical catalyst, drastically altering the chain of nuclear reactions. Specifically, they could have provided a new pathway for lithium-7 to be destroyed. The extra neutrons would have been captured by the lithium nuclei, transforming them into unstable isotopes that would rapidly decay into other, heavier elements like beryllium and boron. In essence, the evaporating black holes would have acted as cosmic incinerators, burning away the excess lithium that the Big Bang had produced. This process would have been patchy and chaotic, depending on where and when these tiny black holes died. But over the entire volume of the young cosmos, their cumulative effect could have precisely trimmed the lithium abundance down to the levels we observe today. It is a beautifully elegant solution. The very objects created in the universe's first fraction of a second could have cleaned up a nuclear accounting error just minutes later. The lithium problem transforms from a flaw in our theory into a potential fingerprint, a radioactive signature left behind by the violent deaths of the universe's first and smallest black holes. But what kind of life could possibly exist on such a world? A black hole planet would be a place of perpetual twilight and violent contradiction. Its primary source of heat would not be starlight, but the furious friction of its own existence. The immense tidal forces from the black hole's gravity would constantly stretch and squeeze the planet's interior, generating intense geothermal heat through a process called tidal heating. This could power vast subsurface oceans of liquid water beneath a thick, icy crust, much like the moons Europa or Enceladus in our own solar system. but instead of orbiting Jupiter, this world circles an abyss. The sky would be dominated by the brilliant, swirling accretion disk, a permanent, blazing aurora of hot gas and dust that never sets, casting an eerie, shifting glow across the landscape. There would be no day-night cycle as we know it, only the constant hypnotic whirl of doomed matter. Life here would evolve in a fundamentally alien rhythm, perhaps deep within the planet's crust or in those pitch-black oceans, sustained by chemical energy from hydrothermal vents heated by the black hole's relentless pull. It is a haunting possibility. The most ancient objects in the universe, the primordial black holes, might not be barren tombs. They could be dark suns, gravitational furnaces around which entire ecosystems of exotic life have arisen, living out their entire history in the ghostly light of a cosmic vortex, completely independent of the warmth of any star. The search for antimatter in the cosmos is a hunt for cosmic ghosts. These are particles identical to normal matter but with opposite charge, and when they meet their ordinary counterparts, they annihilate in a flash of pure energy. We know antimatter exists, but finding where it comes from in deep space is a major puzzle. One of the strangest clues is the positron excess. Positrons are the antimatter twins of electrons. High-energy cosmic rays, which constantly rain down on Earth from all directions, contain a surprising overabundance of these positrons. Instruments like the Alpha Magnetic Spectrometer on the International Space Station have confirmed it. There are simply too many positrons arriving at Earth than our standard models can explain. Something out there, relatively nearby in our galactic neighborhood, must be producing them. Theory number 8 points a finger at a source born in the universe's first instant. Primordial black holes, in their final, evaporating moments, could be prolific antimatter factories. Remember Hawking radiation. As a black hole evaporates, it does not just emit random particles, it emits particle-antiparticle pairs. For a tiny primordial black hole nearing the end of its life, this process becomes a runaway explosion. In its last microseconds, it would flood its surroundings with a burst of radiation and, crucially, a torrent of antimatter particles, including positrons. These antimatter particles, born from the death scream of a cosmic fossil, would then be accelerated by the chaotic magnetic fields of the galaxy, eventually joining the stream of cosmic rays that washes over us. This provides an elegant explanation for the positron excess. We would not need to invoke exotic astrophysical objects like pulsars or dark matter particle collisions as the sole source. Instead, the excess could be the collective final breath of numerous small, ancient black holes popping off like firecrackers throughout the Milky Way's history. The signal we detect would be a diffuse background, a steady drizzle of antimatter from countless tiny, silent explosions happening all around us. It is a haunting thought. The high-energy positrons striking our detectors might carry with them the last signature of objects that witnessed the birth of everything, their final act of evaporation now writing its signature across the sky in particles of anti-stuff. Our understanding of the universe's expansion is facing a profound crisis. For over a decade, two of the most trusted methods for measuring how fast the cosmos is growing have returned stubbornly different answers. It is known as the Hubble tension, and it suggests one of our most fundamental cosmic yardsticks might be broken. Theory 9 proposes that the fix lies in the ghostly afterglow of long-dead primordial black holes. To see why, we need to understand the two conflicting measurements. One method looks at the local universe. Astronomers use pulsating stars called cepheids and cataclysmic supernova explosions in nearby galaxies as standard candles. By knowing their true brightness and measuring how dim they appear, we can calculate distances and speeds with incredible precision. This local measurement gives us a specific high number for the expansion rate. The other method looks back to the infant universe. It uses the cosmic microwave background, the faint afterglow of the Big Bang itself, as a snapshot of the cosmos when it was just 380,000 years old. By meticulously analyzing the subtle patterns in this ancient light, scientists can extrapolate forward, predicting what the expansion rate should be today. This prediction gives us a lower number. The two numbers should agree. They do not. The gap is significant, and it persists despite ever more precise observations. This is not a small error. It is a direct contradiction that could mean something crucial is missing from our model of cosmic history. Enter the primordial black holes. The key idea here involves energy injection. If a vast population of small primordial black holes existed in the early universe, they would not have lasted forever. As we have discussed, they would have evaporated via Hawking radiation, with the smallest ones dying off first. Their final moments would have been violent, releasing bursts of energy and radiation into the surrounding cosmic soup. This extra energy injection is not accounted for in the standard model that we use to interpret the cosmic microwave background. That model assumes a smooth, predictable transition from a hot, dense state to the cooler, expanding universe we see today. But if countless tiny black holes were popping off like a cosmic fireworks show during this critical era, they would have subtly reheated the universe. Think of it like trying to bake a cake while someone keeps opening the oven door. The heat inside fluctuates, the cooking process changes. In the cosmic sense, this extra, sporadic heating from evaporating black holes would have altered the way particles interacted with light in the early universe. This, in turn, would change the precise fingerprint imprinted on the cosmic microwave background. When scientists use that altered fingerprint to calculate forward to today's expansion rate, they might arrive at a different number, one that could potentially align with the higher rate measured in our local neighborhood. The evaporated black holes would be long gone, their energy dissipated across the cosmos billions of years ago. But their brief, explosive influence could have left a permanent mark on the universe's expansion history, a hidden adjustment that reconciles our two conflicting views of cosmic growth. The Hubble tension, therefore, might not be a sign that our physics is wrong, but a clue that we have overlooked the explosive deaths of the universe's first and smallest inhabitants. The silent ripples in space-time carry stories of ancient violence. Our gravitational wave observatories, LIGO and Virgo, have opened our ears to the universe's most cataclysmic events, listening to the final, spiraling dance of black holes before they collide. Most signals fit a familiar pattern, the merger of two black holes born from massive stars, but Theory 10 suggests a hidden symphony within the noise. Some of these cosmic tremors might not be the death cries of stars at all. They could be the long-awaited mergers of primordial black holes, carrying a direct message from the universe's infancy. The key to spotting them lies in their strangeness. Black holes formed from stars follow certain rules, born within a limited range of masses, and often with similar sizes and aligned spins, a legacy of their shared origin in a binary star system. Primordial black holes, forged in the random chaos of the Big Bang, would play by no such rules. They could have any mass, from a tiny asteroid to many times that of our Sun. This means their mergers could produce gravitational waves with bizarre signatures. Imagine a collision between a black hole 50 times the mass of our Sun and a partner only 5 times the solar mass, a wildly uneven pairing unlikely to arise from two normal stars. Or consider their spins. Stellar black holes often spin in the same direction, a memory of their orbital dance. Primordial black holes, having wandered the cosmos alone for billions of years, would have spins oriented completely at random, like two tops thrown together from opposite sides of a room. When such mismatched, chaotically spinning objects finally meet, the gravitational wave signal they produce has a distinctive, messy fingerprint. Detecting these oddball mergers would be a revolutionary discovery. It would be like finding a perfectly preserved fossil in a layer of rock where it simply does not belong. Each unusual signal would be a direct snapshot of conditions in the first fraction of a second after the Big Bang, a moment otherwise completely inaccessible to us. By studying the masses and spins encoded in those space-time ripples, we could literally weigh the density fluctuations of the newborn cosmos. This turns gravitational wave astronomy into a time machine, allowing us to probe an era long before the first stars flickered on, listening to the echoes of the universe's first structures collapsing into darkness. Every new chirp from the cosmos is now a potential message in a bottle, and some of those bottles may have been sealed at the very dawn of time. The fabric of space-time itself may have once been tangled with cosmic threads. Beyond the familiar particles and forces, some of the most profound theories of physics predict the existence of one-dimensional defects, flaws woven into the very structure of reality during its rapid cooling from the Big Bang. These are cosmic strings, theoretical filaments of pure energy thinner than a proton but stretching across the entire observable universe, with the mass of a mountain range packed into every inch. Their existence remains unproven, but if they were real, they would have been engines of incredible violence. And from that violence, Theory 11 suggests primordial black holes could have been born in a uniquely precise way. The process hinges on a cosmic catastrophe. A cosmic string under immense tension is not a static line. It can vibrate, whip, and tangle. When two segments of a string cross, or when a loop of string pinches off from the main filament, something extraordinary happens. The loop can collapse under its own tremendous gravitational pull, but because a cosmic string is a flaw in space-time itself, this collapse is not like a cloud of gas coming together. It is more like a flaw in a crystal suddenly concentrating, a kink in reality snapping shut. The mathematics show that when such a loop collapses, it does not form a black hole of just any random size. The mass of the resulting black hole is directly proportional to the length of the string that formed the loop. This creates a startling prediction. If primordial black holes were formed from cosmic strings, they would not have a smooth distribution of masses. Instead, they would come in very specific, discrete sizes like notes on a cosmic scale. All black holes from loops of a certain length would have one mass. All from loops twice that length would have exactly twice the mass, and so on. This is a fingerprint unlike any other formation mechanism. Finding evidence for such a precise mass distribution among primordial black holes would be a double discovery. It would not only confirm their existence but also provide the first direct proof of cosmic strings, offering a breathtaking link between the world of the unimaginably small, high-energy particle physics and the grand architecture of the cosmos. It would mean that the darkest objects in the universe are direct descendants of the most exotic defects in space-time, a hidden harmony between the quantum and the cosmic written in the mass of ancient shadows. Every black hole we have ever observed shares a violent stellar heritage. They are tombstones, the collapsed cores of giant stars that exhausted their fuel and died in supernova explosions. But this lineage presents a cosmic chicken and egg problem. The first stars needed to live, burn, and die to create the first stellar black holes. Yet those same first stars needed to form in a universe without any prior generations, without the heavy elements and complex structures that help modern stars ignite. So where did the very first black holes come from? Theory 12 proposes a radical family tree. Primordial black holes are not the children of stars. They are the parents, they are the original black holes forged in the universe's first second, long before the first star ever flickered to life. Their birth was not a stellar death but a cosmic birthright. In the searing heat and density of the Big Bang's immediate aftermath, space was not perfectly smooth. Quantum fluctuations, tiny random wrinkles in the fabric of reality, were stretched to enormous sizes by a period of hyper-fast expansion called inflation. Some regions became slightly denser than others. In the most extreme of these overdense pockets, gravity won an instant victory. There was no time for nuclear fusion, no time for a star to form and shine. The matter in these regions was so densely packed, and the universe so incredibly hot and compressed, that it collapsed directly under its own weight. One moment it was a knot in the primordial soup, the next it was a singularity, a black hole born from pure density. This direct collapse mechanism is fundamentally different from the stellar process we know. A star forms a black hole only after a complex billion-year life cycle, fighting against gravity with the outward pressure of nuclear fusion until it finally loses. A primordial black hole skipped the entire life cycle. It was born from a raw lump of the universe itself, a fossil of its initial conditions. This makes them true relics, artifacts from an era before atoms, before light, before anything we would recognize as structure. If this theory is correct, then every stellar black hole, every supermassive giant at a galaxy's heart, is a descendant. The primordial ones came first, the original seeds of darkness from which all later structures in some way grew. They are not the end result of stellar evolution, but its ancient and necessary prerequisite, the dark foundation upon which the luminous universe was built. Dark matter has always been painted as a ghost, a substance that feels gravity but ignores everything else. It is the ultimate passive participant, a silent spectator that shapes galaxies without ever touching the stage. But what if that picture is wrong? What if dark matter is not a featureless sea of identical particles, but a bustling population of ancient objects with their own complex lives? Theory 13 proposes exactly that. Primordial black holes could act as dark matter particles with a rich internal physics all their own. This transforms dark matter from a smooth, invisible fluid into a churning, interactive substance. The key is in their variety. Unlike a hypothetical particle like the WIMP, which would be identical in every way, a population of primordial black holes would have a spectrum. They would be born with a wide distribution of masses, from mountain-sized specks to objects heavier than stars. They would also spin, each with its own unique rotation, a memory of the chaotic whirl of the early universe. This diversity is not just a detail, it is the engine for an entire hidden ecology. With such a range of sizes and spins, these ancient black holes would interact with each other in fascinating ways. They could gravitationally capture one another, forming binary systems that silently orbit through the Milky Way's halo for billions of years. These dark duos would be completely invisible, yet their gravitational influence would be subtly different from a single, solitary object. Over immense timescales, the orbits of these binary black holes would decay through the emission of gravitational waves, leading to mergers. This means dark matter would not just sit there. It would occasionally collide, ripple spacetime, and reorganize itself. This introduces the concept of dynamical friction. Imagine a massive primordial black hole, one with the heft of a star, moving through a cloud of its smaller cousins. Its immense gravity acts like a gravitational wake, pulling the smaller objects toward it and slowing the larger one down, much like a boat moving through water. This process transfers energy and can cause larger black holes to sink toward the centers of dark matter halos, while the smaller ones get scattered outward. The result is a dark matter structure that is lumpy and layered, not smooth. On the scale of a galaxy, this could have profound effects. It might explain why the dark matter halos around dwarf galaxies seem denser in their centers than our computer simulations predict. The models assume a simple, non-interacting fluid, but if the dark matter is made of objects that can cluster and sink, the cores of these halos would naturally become denser. It could also influence how galaxies merge. When two galaxies collide, their dark matter halos are thought to pass through each other like ghosts. But if that dark matter is sticky due to these complex gravitational interactions between primordial black holes, the merger process could be slower, leaving different imprints on the shapes of the resulting galaxies. This theory turns the dark sector from a boring monologue into a dynamic conversation. The darkness would be alive with silent orbits, distant captures, and occasional unions, a hidden dance of ancient relics that has been choreographing the structure of the visible universe from the shadows all along. The hunt for these cosmic phantoms requires watching for the bending of light itself. Theory 14 suggests we can find primordial black holes by the shadows they cast, not by blocking light but by warping it. This technique is called gravitational microlensing, and it is our most powerful tool for searching for these invisible objects. The principle is elegant. According to Einstein's theory of general relativity, a massive object bends the fabric of spacetime around it. Light from a distant star traveling through this warped space does not travel in a straight line. It curves. If a compact, dark object like a primordial black hole passes directly between us and that background star, it acts as a gravitational lens. The black hole's intense gravity focuses the star's light, causing it to brighten temporarily in a very specific way. The star does not simply flicker on and off. It smoothly increases in brightness to a peak, then symmetrically fades away over a period of time that directly reveals the mass of the invisible lens. A heavier black hole will create a longer duration brightening event, a lighter one a shorter flash. For decades, ambitious sky surveys have been staring at dense star fields, like the bulge of our Milky Way or the neighboring Magellanic Clouds, monitoring millions of stars night after night, searching for these telltale flashes. Projects like the Optical Gravitational Lensing Experiment, known as OGLE, have been pioneers in this meticulous work. Their results are fascinating but also deeply constraining. They have detected numerous microlensing events, proving that compact, dark objects are indeed drifting through the galactic halo. However, the duration of these events suggests the lenses are typically around half the mass of our Sun. This has placed severe limits on one possible population of primordial black holes. It tells us that black holes in the mass range of large planets to several times the mass of Jupiter cannot make up all of dark matter. If they did, we would be seeing countless microlensing events every day. We are not, but this does not rule them out entirely. It simply carves away a section of the possible mass spectrum. Primordial black holes could still be abundant if they are either much lighter, like small asteroids, whose lensing flashes would be too brief and faint to detect with current surveys, or much heavier, perhaps tens of solar masses or more, whose lensing events would last for years and be harder to distinguish from variable stars. So microlensing acts as a cosmic sieve. It has filtered out one range of possibilities, forcing the hunt to continue at the extremes. Every unexplained flash in these vast datasets is a candidate, a momentary brightening that could, against all odds, be the signature of a dark wanderer from the beginning of everything, caught in the act of twisting a star's light into a temporary beacon. The universe's most powerful explosions might have the quietest beginnings. Gamma-ray bursts are the single brightest electromagnetic events known to exist, brief but unimaginably violent eruptions that can outshine entire galaxies for a few fleeting seconds. We have categorized them into two broad classes. Long bursts lasting more than 2 seconds are linked to the catastrophic deaths of massive stars, but the short bursts lasting less than 2 seconds are a deeper mystery, often associated with the collisions of neutron stars. Theory 15 suggests there is another, more ancient source for these cosmic fireworks. The final, explosive evaporation of a tiny primordial black hole could unleash a gamma-ray burst of staggering intensity. To understand this, we need to revisit the end of a small black hole's life through Hawking radiation. A black hole is not a perfect vacuum. Quantum mechanics tells us that empty space is a seething sea of virtual particles, constantly popping into and out of existence. At the very edge of a black hole's event horizon, something peculiar can happen. One of these virtual particles can fall in while its partner escapes. From our perspective, the black hole has just emitted a particle. This process steals a tiny amount of the black hole's mass. For a stellar mass black hole, this trickle of radiation is so slow it is utterly negligible, taking timescales longer than the current age of the universe to have any effect. But for a primordial black hole with the mass of a small mountain or an asteroid, the story is completely different. Its much smaller size means its Hawking radiation is far more intense. It loses mass faster, which makes it even smaller, which in turn makes it radiate even faster. This creates a runaway process, a thermal runaway. As the black hole shrinks, its temperature skyrockets. In its final moments, it is no longer emitting a faint whisper of particles. It is screaming. The evaporation accelerates into a violent, catastrophic explosion. The tiny object, now hotter than the core of a star, releases all of its remaining mass energy in a fraction of a second. This final burst is not composed of gentle light. It is a torrent of the highest energy photons in existence, gamma rays. The energy profile of this death scream matches the characteristics of a short gamma ray burst remarkably well. It would be an incredibly brief, intensely focused beam of radiation, appearing from nowhere and vanishing just as quickly, leaving no lingering afterglow like a supernova would. There is no stellar remnant, no expanding nebula, just a silent patch of space where an ancient relic once was. For astronomers, detecting such an event would be a monumental challenge, but also a potential revelation. We would need to catch a flash that is intrinsically very faint compared to a neutron-star merger happening in a distant galaxy, because a primordial black hole evaporating would likely be much closer, perhaps even within our own Milky Way. Its signal would be clean and simple, a pure spike of gamma rays without the accompanying gravitational wave chirp or the kilonova glow of heavy elements that marks a neutron-star collision. Finding one would be like hearing a single, deafening gunshot in an empty forest with no shooter and no bullet to be found. It would be the definitive signature of an object from the first second of time meeting its end in our modern epoch, a final, brilliant flash that writes its own epitaph across the gamma-ray sky. The cosmic web is the largest structure in existence, stretching across billions of light years. It is a vast, delicate network of galaxy clusters connected by gossamer filaments, with immense, empty voids in between. This grand architecture is the ultimate legacy of gravity, sculpted over nearly 14 billion years, but there is a lingering tension in the story of how it all came to be. Our best supercomputer simulations, which model the growth of structure from the smooth, early universe, produce a cosmic web that is remarkably similar to the one we observe. Yet, they often struggle on smaller scales. They predict more small, satellite dwarf galaxies around large galaxies like the Milky Way than we actually see, and the dark matter halos they generate tend to be less dense in their centers than real observations suggest. These are the small-scale structure problems. Theory 16 proposes a powerful solution, one rooted in the earliest moments of time. Primordial black holes could have jump-started the entire process of cosmic construction. The standard model relies on cold dark matter, a smooth, passive fluid that only begins to clump under its own gravity after the universe has expanded and cooled for a long time. But what if the seeds for clumping were already there from the very beginning? That is the revolutionary idea. Imagine the universe just moments old, still a seething, opaque plasma. Scattered throughout this primordial soup are countless primordial black holes, a population born from the densest quantum fluctuations. They are not smooth. They are discrete, ultra-dense points of mass. Each one is a ready-made gravitational nucleus, a tiny pit in the fabric of space-time. In a universe filled with these dark seeds, structure formation does not have to start from scratch. It has a head start. These black holes, especially the more massive ones, immediately begin to attract the surrounding dark matter and ordinary matter. They act as anchors around which the first dark matter halos can coalesce with incredible speed. This early, aggressive clumping could explain why we see such large, mature galaxies and quasars in the very early universe. They simply had more substantial foundations to build upon, but the influence goes deeper, addressing those small-scale issues. In the standard smooth dark matter model, small structures are easily wiped out by later cosmic events like the heating from the first stars. This process, called suppression, might erase too many of the small dwarf galaxies. Primordial black holes change the game. Because they are discrete, hard points of immense density, the structures they seed are more robust, more resilient. A small halo anchored by a primordial black hole is like a stone in a stream, while a halo formed from smooth dark matter is more like a clump of sand. The stone holds its shape against the current. This resilience could allow more small satellite galaxies to survive to the present day, potentially bringing theory into better alignment with the actual sparser population we observe around the Milky Way. Furthermore, the very nature of these dark matter anchors could lead to denser central cores in halos. A massive primordial black hole sitting at the center of a developing dwarf galaxy would naturally create a steep gravitational well, pulling in more dark matter and creating the kind of dense central profiles that some observations suggest. The cosmic web in this view is not woven from a smooth, featureless thread. It is embroidered around a pre-existing pattern of dark knots, each one a silent, ancient artifact from the first tick of the cosmic clock. The grand design of the universe, therefore, might trace its blueprint back to a random scatter of quantum dots, magnified by inflation into the gravitational seeds for everything we see. Our cosmic census of black holes has revealed a curious emptiness, a forbidden zone where nature seemed to forbid their existence. Astronomers call it the upper mass gap. On one side, you have neutron stars, the collapsed cores of dead stars, with a firm upper limit around 2.5 times the mass of our Sun. Any heavier, and they collapse into a black hole. On the other side, you have stellar black holes starting at around 5 solar masses. For years, the space between roughly 3 and 5 solar masses was a desert, seemingly devoid of compact objects. The physics of stellar core collapse appeared to make objects in this range extremely rare. Then our gravitational wave detectors began listening. The very first merger LIGO ever heard, back in 2015, involved a black hole of about 36 solar masses and a partner of 29. But as the observatories grew more sensitive, they started hearing whispers from smaller pairs, and then came the puzzle. In 2019, a signal arrived from a merger where one object was about 23 solar masses, but the other was just 2.6. That placed it squarely in the mass gap, too heavy to be a neutron star, yet too light to fit the traditional model of a stellar black hole. Around the same time, using traditional telescopes, astronomers found a strange object in our own galaxy, nicknamed the Unicorn. It is a red giant star that is being subtly tugged by an unseen companion. The data suggests this dark partner is only about 3 solar masses, again, sitting right in that forbidden zone. Theory 17 proposes a beautifully simple explanation for these oddballs. They are not misfit stellar remnants struggling to exist. They are primordial black holes filling in the mass spectrum naturally. Remember, black holes forged in the Big Bang's chaos would not care about the rules of stellar evolution. They would be born with a wide, smooth distribution of masses from the tiny to the tremendous. The apparent gap is not a law of nature for them, it is merely an artifact of how stars die. A primordial black hole could easily have a mass of 3 or 4 or 4.5 solar masses. It would have carried that weight for 13.8 billion years, a silent wanderer that only now, through a chance merger or a gravitational dance with a star, has revealed its presence. Finding these objects in the gap is like discovering a living dinosaur in a modern forest. It does not fit the current ecosystem because it is a relic from a much earlier time. The unicorn and its kin, therefore, might be our first direct samples of the primordial population, objects that bypassed stellar life entirely and have been drifting through the galaxy since its infancy. Their existence would instantly solve the mass gap mystery. not by changing the rules of stellar physics, but by showing us that the cosmos has always had another, more ancient way of making darkness. Their formation might not have involved matter as we know it at all. The deepest laws of physics suggest the newborn universe was a far stranger place than we can conceive, filled with exotic states and fields that have long since faded from existence. Theory 18 ventures into this speculative frontier, proposing that primordial black holes were not born from collapsing hydrogen or radiation, but from the death of something far more bizarre. They could be the remnants of theoretical objects called cue balls. To grasp this, we need to step into the realm of supersymmetry, a leading candidate for physics beyond the standard model. This theory predicts a zoo of new particles and, crucially, stable configurations of energy known as scalar fields. A cue ball is a hypothetical lump or soliton made entirely from such a field. Think of it not as a clump of atoms, but as a coherent bubble of pure potential energy, a stable knot in the fabric of reality itself. In the extreme energies of the very early universe, such cue balls could have formed abundantly. Unlike any overly dense object, if a cue ball grew too massive or became unstable, it could have undergone gravitational collapse, but this collapse would be fundamentally different. It would not be ordinary matter falling inward. It would be a pocket of exotic physics imploding, potentially creating a black hole with properties unlike any formed from stars. These cue ball black holes might have unusual stability or even different evaporation rates compared to their standard cousins. Their event horizons could, in theory, be threaded by the lingering imprint of the scalar field that birthed them. Most intriguingly, this formation mechanism provides a natural and robust way to create black holes across a wide range of masses in the universe's first moments. The exotic physics that governed that epoch would have directly seeded the darkness. If this is true, then every primordial black hole is more than a fossil of density. It is a fossil of a lost state of reality, a frozen moment from when the forces of nature were unified and the cosmos was governed by laws we are still struggling to comprehend. Finding one would be like uncovering an artifact not just from an ancient time, but from an entirely different version of physics. A star's heart is a relentless fusion reactor, fusing hydrogen into helium in a battle against its own crushing gravity. But what if that fiery core was replaced by something else, something dark and ancient? Theory 19 proposes a stellar imposter, a star hiding a primordial black hole at its very center. This is not a star being consumed from the outside. It is a star being powered from within by a dark engine. Astronomers call this hypothetical object a Hawking star. The formation would be a cosmic capture, a small primordial black hole, perhaps with the mass of an asteroid or a planet, drifts through a cloud of interstellar gas. As it moves, its gravity gathers material, eventually triggering the collapse and ignition of a normal star. But instead of forming a nuclear fusion core, the newborn star forms around the black hole. The black hole now sits at the star's center, a tiny, insatiable pit. It begins to slowly accrete matter from the star's interior. This infalling material, heated to incredible temperatures as it spirals into the event horizon, releases vast amounts of energy. This energy, radiating outward, provides the pressure needed to support the star's outer layers against collapse. In essence, the black hole becomes the star's power source, replacing nuclear fusion. The implications are profound. A Hawking star could look deceptively normal from the outside. It might shine with a steady light, mimicking a red giant or another long-lived phase of stellar evolution. But its internal workings would be completely alien. It would be cooler at its core than a fusion-powered star, and its composition would be different, lacking the heavy elements forged in a traditional nuclear furnace. It could live for an extraordinarily long time, far exceeding the lifespan of a normal star, because its dark heart is not limited by a finite fuel supply of hydrogen. It can feed on the star itself for billions, even trillions of years. This creates a stellar zombie, a star that appears alive but is animated by a corpse from the dawn of time. Detecting one of these cosmic masquerades would be a monumental challenge. Its light spectrum might hold subtle clues, a missing signature of certain nuclear processes or an unusual temperature profile. Or we might notice its strange longevity, a star in a region where all its peers have died, yet it continues to shine with an eerie persistence. Finding a Hawking star would be a discovery of existential elegance. It would mean that the oldest objects in the universe are not just drifting in the void. Some of them have found a home, nestled inside the very hearts of stars, where they burn not with fire, but with the silent, gravitational hunger of the primordial dark. Magnetic fields are woven through the fabric of the cosmos. They thread through galaxies, guide the flow of interstellar gas, and shape the birth of stars. But their origin is a profound mystery. How did these invisible lines of force stretching across millions of light years first come to be? Theory 20 proposes a surprising architect hidden in the earliest darkness. Primordial black holes could have been the universe's first dynamos, generating the seed magnetic fields that everything else amplified. To understand why this is a problem, we need to start with a blank slate. The newborn universe was a smooth, hot plasma. In such a state, any small, initial magnetic fields would have been quickly scrambled and erased, like trying to draw a straight line in boiling water. Yet today, we see coherent magnetic fields everywhere we look. Something had to create the first organized magnetic lines, the initial twist in the cosmic fluid, for later processes to build upon. That is where the ancient black holes enter the story. Imagine one of these relics born in the first second. As it moves through the primordial plasma, it does not move alone. It gathers a swirling cloak of superheated gas and a accretion disk around itself. This disk is not a calm, flat ring. It is a turbulent, churning maelstrom of charged particles, electrons and protons ripped apart in the intense heat. In any such system of moving charged particles, magnetic fields can naturally arise and become tangled, a process called a dynamo. The black hole's immense gravity provides the engine, the rotation provides the twist, and the hot plasma provides the conductor. This creates a localized but incredibly intense magnetic bubble around each black hole. But a single, isolated magnetic bubble is not enough. The genius of this theory lies in the population. If primordial black holes were abundant, especially in the early universe, then space would have been dotted with billions upon billions of these microscopic dynamos. Each one, like a tiny, spinning magnet, would have imprinted its own magnetic field on the surrounding gas. As the universe expanded, these fields would have been stretched and woven together. When the first galaxies began to form, collapsing around the gravitational seeds of the most massive black holes, they would have drawn in this magnetized gas. The chaotic motions within the young galaxy would then have acted like a gigantic amplifier, taking those faint primordial magnetic threads and twisting them into the powerful, large-scale fields we observe today. It is a cosmic relay race. The baton of magnetism is passed from the quantum fluctuations of the Big Bang to the violent dynamos of the first black holes, and finally to the turbulent hearts of newborn galaxies. Without that initial, widespread seeding, it is difficult to explain how magnetic fields became so universal so quickly. This idea gains even more intrigue if some of these primordial black holes were born with a slight electric charge, a possibility in some exotic early universe models. A charged black hole moving through plasma would be a magnetic field generator in its own right, like a cosmic bar magnet sailing through a conductive sea, leaving a trail of magnetized space in its wake. So the next time you hear about the magnetic field of a distant galaxy, remember it might not be a local phenomenon. Its roots could reach back to a hidden population of dark engines spinning in the dawn of time, whose first whispers of magnetism were amplified into the cosmic chorus we detect today. The faintest light in the universe holds the deepest secrets. The cosmic microwave background is more than just an afterglow. It is a fossilized snapshot of the cosmos when it was just 380,000 years old, a time before stars or galaxies. Every subtle variation in its temperature, every twist in its polarization, is a message from the dawn of time. And Theory 21 suggests that future experiments might find a new kind of signature etched into this ancient light, one written by the explosive deaths of the universe's first inhabitants. Next-generation observatories like the Simons Observatory and the ambitious CMB-S4 project are not just upgrades. They are time machines with exponentially sharper vision, designed to map the microwave sky with a sensitivity and detail we can barely imagine today. They will look for more than just the wrinkles that seeded galaxies. They will hunt for the faintest scars, the spectral distortions and unique polarization patterns that could only come from a violent energy injection into the primordial plasma. This is where primordial black holes enter the picture. If a vast population of small black holes evaporated in the first few 100,000 years of the universe, as Hawking radiation predicts, their final moments would have been spectacular. Each tiny explosion would have dumped a burst of high-energy photons and particles into the surrounding soup of electrons and protons. Think of it like dropping a hot stone into a still pond. The stone itself vanishes, but it sends ripples across the entire surface, changing the water's temperature and motion in a specific way. In the cosmic pond, that energy injection would have done two critical things. First, it would have slightly reheated the electrons in the plasma, creating a specific, subtle distortion in the blackbody spectrum of the microwave background. It would be a tiny deviation from perfect thermal equilibrium, a ghostly fingerprint of countless micro-explosions. Second, and perhaps more telling, it would have scrambled the polarization of the light. The CMB's polarization is a record of the last time photons scattered off electrons. A sudden blast of energy from an evaporating black hole would have stirred up that plasma, altering the pattern of those final scatterings. The resulting polarization signal would be non-Gaussian, meaning it would have statistical oddities and specific patterns that don't fit the standard model of smooth quantum fluctuations. These imprints would be incredibly faint, buried deep in the noise of the cosmos, but the new observatories are being built precisely to find such whispers. They will analyze the microwave sky with such precision that they could detect the collective death rattle of an entire generation of primordial black holes. If they find these spectral distortions or these strange polarization swirls, it would be indirect but incredibly powerful evidence. We would not be seeing the black holes themselves. We would be seeing the aftermath of their final, fiery moments, a permanent scar on the universe's oldest photograph. It would be proof that the first seconds of time were not just smooth and hot, but punctuated by the silent pops of dark relics meeting their end, their energy forever encoded in the first light to ever travel freely through the cosmos. The cosmic microwave background should be a perfect random tapestry. Its hot and cold spots, the frozen echoes of quantum noise from the Big Bang, ought to point in every direction with no preferred alignment. Yet, when cosmologists map it with exquisite precision, they find something unsettling. The largest scale fluctuations seem to whisper of a direction, a faint but statistically significant alignment along a particular line in the sky. Scientists have dubbed this eerie feature the axis of evil, a name that captures both its mystery and its threat to our standard model of cosmology. Theory 22 ventures into this strange territory, suggesting the axis is not a flaw in the cosmos but a shadow. It could be the gravitational imprint of a vast, coherent river of primordial black holes streaming through the infant universe. To understand how, picture the moment the cosmic microwave background was released. 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and light broke free, beginning its 13.8 billion-year journey to our telescopes. That light carries a perfect snapshot of that instant, But what if, just before that light was set free, something immense passed by, a colossal structure not of galaxies but of ancient darkness? Imagine a filament, a flowing river composed of countless primordial black holes, all moving in the same general direction through the primordial plasma. Such a structure, born from an exceptionally large, stretched quantum fluctuation during inflation, would possess staggering mass and coherence. As the last scattering photons began their journey, they would have had to pass through the gravitational field of this dark river. General relativity tells us that massive objects bend light. This river, acting as a titanic gravitational lens, would have subtly distorted the pattern of hot and cold spots on the cosmic microwave background. It would not create new spots, but it would stretch and shift the existing ones in a specific, directional way. The effect would be like looking at a patterned wallpaper through a giant, slightly warped magnifying glass that is moving in one direction. The pattern itself is random, but the distortion imposed upon it has a preferred axis, the direction of the lens's flow. This could imprint exactly the kind of large-scale alignment that makes the axis of evil so perplexing. The anomaly would not be in the initial conditions of the universe, but in something that happened to its first light on the way to us. It is a cosmic smudge on the window of time, left by a passing shadow of unimaginable age. This idea transforms the axis of evil from a statistical ghost into a potential fossil of the first large-scale structure ever to exist. It would mean that even before the first stars, before the first atoms, the universe was already organized on a grand scale, not by glowing gas, but by a silent, flowing architecture of primordial darkness. Finding corroborating evidence would be extraordinarily difficult but not impossible. Such a massive stream of black holes would still exist today, threading through the cosmic web. Its gravitational influence might subtly shear the shapes of distant galaxies along that same cursed axis, or affect the peculiar motions of entire galaxy clusters. We would be searching for the present-day ghost of a structure that left its mark on the universe's baby picture. If found, it would be the ultimate cold case solved, revealing that the spookiest anomaly in all of cosmology is just the lingering fingerprint of the first river of shadows forever flowing across the sky. A quiet revolution in astronomy began by staring at a neighboring galaxy. The MACHO project, which stands for Massive Compact Halo Objects, was a bold experiment in the 1990s. Its goal was simple yet profound. It aimed to solve the dark matter puzzle by looking for the unseen masses within our own galaxy's halo, the vast spherical cloud of matter that surrounds the Milky Way. Their method was the same gravitational microlensing technique we discussed earlier. For years, they meticulously monitored millions of stars in the Large Magellanic Cloud, a small satellite galaxy of our own. The idea was that if our galaxy's halo was filled with compact, dark objects like faint stars, brown dwarfs, or black holes, they would occasionally drift in front of these background stars, causing the telltale brightening flash. And they found them. The project detected dozens of these microlensing events. The data suggested something was definitely out there, a population of invisible, compact objects with masses roughly between 1/10 and 1 times the mass of our Sun. This was a monumental discovery. It proved that a fraction of our galaxy's dark halo was indeed made of MACHOS, but there was a problem. The number of events they saw, while significant, was not enough to account for all of dark matter. The MACHOS could only explain a portion of the Milky Way's missing mass, perhaps around 20%. So what were they? The project could not identify the nature of the lenses. They could have been old, burned-out white dwarf stars or rogue planets or neutron stars, but one compelling candidate has always lingered in the background. Theory 23 revives this mystery with a modern twist. Those detected MACHOS could be a specific population of primordial black holes. The mass range fits beautifully. A primordial black hole with the mass of Jupiter would be far too light to create a detectable lensing event in that survey. One with the mass of 100 suns would be too heavy, creating an event lasting decades. But a black hole with half the mass of our Sun, that creates a microlensing flash that lasts for weeks or months, exactly the duration range the MASCHO project observed. This creates a fascinating possibility. Primordial black holes may not be a monolithic population that makes up all of dark matter. Instead, they could exist in specific mass windows like islands in a vast sea. The MASCHO results could have been detecting one of those islands, a specific family of primordial black holes born with masses similar to stars. These objects would be drifting silently through the galactic halo, too dark to see, too compact to be anything but a black hole or a similar remnant, and just the right mass to bend light in a way we caught a glimpse of 30 years ago. Modern constraints from other microlensing surveys and gravitational wave data have narrowed the possibilities, but they have not ruled out this specific mass range. So the legacy of the MASCHO project endures, not as the final answer to dark matter, but as a potential sighting of something even more profound. Every one of those recorded flashes might have been the momentary unveiling of an ancient wanderer, a black hole from the beginning of time, caught in the act of casting a shadow we were clever enough to see. The early universe was a place of radical transformation. As it expanded and cooled, it did not do so smoothly like a pot of soup left on the counter. It underwent sudden, violent changes of state, like water freezing into ice. Physicists call these cosmic phase transitions, moments when the fundamental forces of nature split apart and the very rules of reality rewrote themselves. One of the most pivotal was the electroweak transition, when the electromagnetic force and the weak nuclear force became distinct. Theory 24 ventures into this seething, primordial chaos with a bold claim. Primordial black holes could have been forged in these transitions, and their birth might have violently reshaped the cosmos. To grasp this, picture the universe just a picosecond after the Big Bang. Space is filled with a unified, high-energy field, a sort of cosmic syrup. As the temperature drops, this field must settle into a new, stable configuration. But it does not settle everywhere at once. Like bubbles forming in boiling water, pockets of the new phase appear randomly. These bubbles of the new reality expand at nearly the speed of light, colliding and merging until the entire cosmos has transformed. Now, here is where it gets spectacular. At the boundaries where these bubbles collide, immense energy is concentrated. The walls of the bubbles are regions of incredibly high density and tension. In the violent turbulence of these collisions, spacetime itself could have been knotted into singularities. Matter and energy could have been crushed into black holes not by gravity overcoming pressure, but by the sheer violence of the universe changing its mind. This is a formation mechanism of breathtaking elegance. The black holes are not random overdensities. They are fossils of cosmic walls colliding, relics of the moment the weak force went its own way. But their influence would not have ended with their creation. Their formation itself would have released a burst of latent heat, like the energy released when steam condenses back into water. This extra injection of energy would have created new ripples and inhomogeneities in the primordial soup. Think of it like throwing a handful of stones into a still pond just as it's beginning to freeze. The freezing pattern that results is no longer smooth and uniform. It is full of cracks, ridges, and strange textures dictated by the splash of each stone. These new wrinkles would have had profound consequences. They would have provided additional seeds for matter to clump around, potentially accelerating the formation of the first structures. More intriguingly, they could have dramatically influenced particle production. The extreme conditions around these newborn black holes would have been factories for exotic particles, potentially including the very dark matter particles we've been searching for, or even matter-antimatter pairs. In this scenario, primordial black holes are not just passive byproducts of the early universe. They are active participants in its evolution, their violent birth ringing the cosmos like a bell, setting off chain reactions that determined where galaxies would form and what they would be made of. Their shadows, therefore, might be cast not just by gravity, but by the moment the forces of nature themselves chose their separate paths. Our final theory shatters the very notion of a single universe. The most profound explanation for primordial black holes might be that they are not from our universe at all. They could be scars from the birth of our cosmic pocket, or bruises from collisions with other realities entirely. This is the multiverse hypothesis, and it transforms these ancient objects from cosmic fossils into something far stranger. Picture the multiverse not as a collection of separate universes floating in some void, but as an eternally bubbling, frothing sea of space-time. In this endless cosmic foam, new universes are constantly budding off, inflating into their own vast, self-contained bubbles with potentially different laws of physics. Our entire observable cosmos is just one such bubble. Now consider how these bubbles form and grow. The process called bubble nucleation is unimaginably violent. It is a phased transition of reality itself, a sudden, explosive expansion of a new vacuum state. At the instant our bubble universe was born, the energies involved would have been beyond comprehension. In that seething cauldron of creation, the fabric of space-time could have been torn and knotted into singularities directly. Primordial black holes, in this view, would be the birthmarks of our universe, knots tied in the fabric of reality at the moment it came into being. Their distribution and masses would encode the precise conditions of that cosmic genesis, but there is an even more astonishing possibility. In the frothing multiverse, bubbles do not always form in isolation. They can collide. Imagine another universe with entirely different constants and dimensions, expanding until its wall brushes against the wall of our own. The collision would be an event of cataclysmic energy, a shockwave propagating through the newborn plasma of our cosmos. Where that shockwave concentrated, where the fundamental fields of two separate realities met and interacted, the energy density could have been so extreme that it collapsed directly into black holes. These would be true aliens, objects not forged from the matter of our universe, but from the boundary between ours and another. They would carry, frozen within their event horizons, an imprint of that impossible encounter. Finding a population of primordial black holes with a specific, unexpected mass distribution could be the first empirical evidence for the multiverse. It would be a message in a bottle, but the bottle was sealed in a reality adjacent to our own. Every one of these dark relics would then be more than a key to our past. It would be a window into the infinite beyond, a permanent scar that whispers we are not alone in the grand ensemble of all that is. The search for the universe's first black holes ultimately becomes a search for our own cosmic origin story, and perhaps for our neighbors in the unimaginable vastness of the multiverse. From dark matter's ghostly presence to the violent birth of the first stars, the shadow of these ancient objects touches nearly every cosmic mystery we have. They could be the hidden architects of galaxies, the unseen shepherds in our own solar system, and the explosive engines behind the universe's most fleeting signals. Each theory we have explored is a different facet of the same profound idea, that the key to understanding our present cosmos was forged in its first unimaginable second. Primordial black holes remain firmly in the realm of theory, a spectacular hypothesis waiting for its definitive proof. Yet, even as possibilities, they are a testament to human curiosity, a powerful tool that allows us to reach back and probe the very limits of time and physics. They challenge us to look at every unexplained flash, every odd gravitational tug, every lingering cosmological tension, and ask a thrilling question. Could this be the signature of a relic from the dawn of everything? The search continues in the data from gravitational wave observatories, in the next-generation maps of the cosmic microwave background, and in the patient watch for a star's light to briefly flare. Which of these 25 possibilities reshaped your view of the universe the most? Let us know in the comments below, and subscribe to join us as we keep exploring the deepest mysteries waiting in the